Modern processors maintain their massive throughput by predicting future execution paths. To achieve billions of operations per second, a CPU cannot wait for instructions to arrive. It must begin guessing which commands it will need next. This requirement is triggered by conditional branches. In software, these typically manifest as if, while, or for statements, logic gates where the processor must evaluate a condition before choosing one of two distinct memory addresses. When a processor encounters a branch, it faces an immediate performance trade-off. Predicting the outcome correctly allows the CPU to maintain its momentum, but a wrong guess forces hardware to physically discard its recent calculations and restart the sequence. Instruction pipelining maximizes this momentum. By breaking tasks into microstages, fetch, decode, execute, write, the processor handles parts of multiple instructions simultaneously. While executing instruction 1, it decodes 2 and fetches 3. Once saturated, the CPU completes one full instruction every clock cycle. These pipelined architectures became the industry standard for high-performance computing, enabling the massive increase in clock rates seen in processors like the Pentium series. However, this throughput depends entirely on a deterministic sequential flow of data. The pipeline operates under the assumption that the next instruction is always known. While pipelining is the engine of modern CPU speed, the system is fragile. Any interruption to the continuous intake of instructions causes the processor's performance to drop. A conditional branch instruction introduces a structural hazard. It tells the CPU to jump to a new memory address if a condition is met. This creates a timing gap. The CPU cannot confirm the outcome until it reaches the execute stage, several cycles ahead. During this gap, the processor is blind. It has the capacity to load new work, but it cannot confirm which path the program will actually take. These branches break the deterministic flow of the pipeline, creating a hazard that forces the architecture to choose between waiting or gambling. The simplest way to handle this hazard is to halt the fetch stage. The processor simply stops and waits for the condition to evaluate. This generates pipeline bubbles, empty, wasted stages moving through the processor. No computational work is performed while these bubbles occupy the execution units. In modern deep pipelines, which often span 10 to 20 stages, these bubbles can waste dozens of clock cycles for every single branch instruction. Stalling for branch resolution destroys the benefits of parallelism, effectively reverting a high-frequency processor back into a slow scalar machine. To solve this, CPUs utilize a branch prediction unit. This specialized hardware sits near the start of the pipeline and guesses the outcome of a branch before the math is even calculated. The unit analyzes an incoming branch and selects the most likely path based on how that specific branch has behaved in the past. This triggers speculative execution. The CPU immediately fetches and begins processing instructions from the predicted path without waiting for confirmation. Speculative fetching allows the pipeline to remain saturated. By moving forward on a guess, the processor avoids the creation of pipeline bubbles entirely. Under speculative execution, the CPU occupies its execution units and registers with unconfirmed data, performing work before the program has officially reached that point in the code. The speculative instructions continue through the pipeline until the original branch instruction finally reaches the execute stage. In the successful scenario, the hardware confirms that the branch condition matches exactly what the prediction unit guessed. This results in the retire process. The speculative results are validated and permanently written to the system's registers and memory, as if the branch hazard never existed. By not stalling the pipeline, the processor has saved up to 20 clock cycles on this single operation. When the prediction is correct, the CPU maintains its maximum theoretical throughput, rendering the branch instruction functionally invisible to the pipeline's speed. The system fails when the branch reaches the execution stage and the math contradicts the prediction unit's guess. This triggers a pipeline flush. To prevent corruption from incorrect calculations, the CPU must instantly discard all speculatively processed data in the pipeline. The processor resets its program counter and begins fetching the correct instructions from the alternate memory path. This is a severe penalty. The CPU loses 15 to 20 clock cycles of work and is forced to restart the pipeline from a cold stop. While the processor discards the mispredicted logic, the physical act of fetching that data leaves a temporary footprint in the CPU's cache. This subtle hardware trace is the mechanism exploited by Spectre side-channel attacks to observe data that should have remained protected. Because mispredictions are so destructive to performance, speculative execution is only viable if the prediction hardware maintains overwhelming accuracy. To achieve that accuracy, CPUs use a branch target buffer, a specialized cache that maps specific branch addresses to their recent historical outcomes. Each entry in the buffer uses a 2-bit saturating counter as its decision-making engine. When a branch is taken, the counter increments toward the strongly taken state. When it is not taken, the counter decrements. The 4-state system introduces hysteresis, providing a built-in resistance to sudden changes in behavior. Because it uses 2 bits, a branch must act contrary to its current prediction twice in a row before the counter will flip its future guess. This hysteresis prevents a single anomaly, such as the final exit of a long-running loop, from destroying a stable and accurate long-term prediction pattern. These microarchitectural rules explain high-level software anomalies, such as a C++ benchmarking loop evaluating an if x less than 100 condition. In an unsorted array, the data is random, which makes the branch outcomes random. The saturating counter cannot establish a pattern, leading to constant mispredictions and expensive pipeline flushes. But if the array is sorted, all values meeting the condition are grouped together. The 2-bit counter quickly locks into a strongly taken state and maintains 99. Even when the algorithmic logic is identical, raw execution speed is ultimately dictated by how predictable the data appears to the underlying hardware. CPU performance is built on layers of abstraction, from the layout of the silicon up to the high-level code produced by a compiler. Modern processor speed is a carefully maintained illusion, made possible only by parallel staging and the hardware's ability to guess the future. For developers, the final takeaway is that efficient software requires looking beyond Big O notation to write code that respects the mechanical constraints of the processor. Every program that runs today depends on this microscopic gambling machine, continuously attempting to outpace the limits of time.